I hope it is on. Yeah. So first of all, I'd like to ask whether you have got a chance to look at the videos that I have shared, I think on Saturday.
Yes, sir.
Uh,
Sir, yeah. Am I audible? Actually, I'm here with phone.
yeah, you are audible. Yes, you're audible. Okay, good.
Sir, actually, I just wanted to say that I have watched four videos. Before
Mhm,
next class, I will watch the rest. Sir,
mhm.
the audio is a bit low, sir. Actually, I've tried with different headphones also. So, for next videos, is it possible if the audio of the videos can be a bit louder, sir? I've turned
So,
on the caption.
okay, so is it the same for the others? I don't know. I was putting on my headphone and it was, I
Yes,
hope.
actually, if anyone can say that, it will be helpful that if the audio is.
Yes, sir. Audio was very low.
Okay, okay. I'll take care of the things from the next videos. Okay, I'll do that. I'll do that.
Yes,
Okay.
thank you.
Okay, thank you for the feedback. But I don't know. I put on my headphone, it was fine. But yeah, I'll take care of it. Don't worry about it. Okay. So so let us get started. Give me a moment to share the screen. Just give me a moment. So is the front side slide visible? The first slide?
Yes, sir. Visible.
Yes, sir.
Okay,
Yes, sir. Visible.
just yeah, okay, thank you. Let me check other thing. So I am opening my browser. Is it visible?
Yes, sir. Visible.
Yes.
Okay, good. So these are the two things we need. Okay. So so we'll be talking about Prolog today, which we say it's a language for AI. But I'll try to put a disclaimer here on this statement that if we look at AI, we can look at AI in two perspectives. One is the classical AI and the modern AI, right? So whatever we are studying in this course might be categorized into classical AI, where we talk about logic, knowledge-based systems, search, planning, etc. And at this point of time, we have other kind of AI that we talk about, mostly deep learning, machine learning. So this Prolog is a language, I'll say, is a language for the classical AI, where we try to solve problems that can be framed mostly using a search paradigm. So I hope you have already gone through the previous lecture where you have studied search related things like game tree, different algorithms for doing efficient search, right? So we will talk about a language that will follow those kind of paradigms or those kind of algorithmic flavors and try to implement that using a language, right? So Prolog stands for programming logic. So as you see by the name, you can already guess what we are trying to do. Basically, we will be uh, mm, looking at the logical way of inferring the goal as we did earlier, and try to put a programming environment over that idea to solve many problems, as I have stated earlier. So we'll be interested in the problems that are kind of search problems. But again, uh, you cannot see all the problems that can be modeled readily or very easily as a search problem. But we'll see that how we can mm, see model the problems that can be readily translated into a search problem, but yet we can solve them using Prolog, right? So let me lay out the plan for this particular module. So Prolog is a very huge thing. So by no way I'm going to give you a very comprehensive view of Prolog. The basic plan is to provide you the set of features or discuss the set of features that will be useful to get started with. And of course, if you explore more on it, you will get to learn, right? So first of all, let me tell you, it is a kind of different programming philosophy. So I hope that you have all written programming in one or other language, like say C++, Java, Python, something like those, right? So there, if you look at the way we were writing the programs, we had a problem statement, of course, and of course, in the problem statement, we had a goal, and that goal is a kind of different goal that we'll be talking about later, right? Again, you have a problem statement and you are trying to write a procedure, right? So you are trying to, uh, okay. So you are trying to write a procedure. So what is a procedure? Procedure is nothing but a set of instructions that you are writing to solve the problems, right? Uh, Now, the programming philosophy that we are kind of trying to discuss now is a kind of different paradigm. So here, I'll not talk about procedure. I'll not talk about procedure. What I'll be doing, I'll be specifying the intent of what I'll be doing, right? So basically here, we lay out how to solve the problem. So this is very important. Here we are laying out how to solve the problem, but here we are laying out what to solve or what to achieve. Now, one may ask, if we just say what to achieve, how does the computer know that how to solve it, right? So the rest of the part, the how part of it, will be taken care of by the programming environment. Right? And this kind of philosophy of programming is what we call as goal-oriented design. So here what we'll be doing, we'll be specifying a goal like, so now let us demarcate the notion of goal here than the notion of goal that we have talked about in the procedural aspect, right? So here we are talking about goal uh, in connection with the search problems. So what we have, you have an initial state, and by performing a set of operation, you are transiting from one state to another state. And finally, what you want as a solution, you want to reach a state which matches certain constraints or specification. So that is our goal, right? I'm talking about that kind of goal, right? Now, while we talk about this kind of philosophy, there are different languages that came up. These languages, they can again be divided into two parts. One is imperative language and other is declarative language. We'll be talking about them later. So the declarative language is basically what you are declaring. So it is a kind of what kind of language. And in imperative language, you are stating the commands, the exact commands, and here we address the how part of the problem. Right. So basically, we'll be focusing on this philosophy of designing programs. Right. Now, with this, let us go into or look into the connection between Prolog and the logic, the computational logic that we have discussed in the earlier lectures. So Prolog has a very tight connection or a neat connection with logic. First of all, in Prolog, as we proceed forward, we'll see that we need to write a set of rules, and this set of rules are basically the horn rules or horn clauses. So I'd like to ask from anyone you, what do you mean by horn clauses? So perhaps uh, Chavi, can you tell me what is a horn clause?
Sir,
Hello?
yes, sir.
Yeah, what is a horn clause? So can anyone from you volunteer to tell me what is a horn clause?
So it is
Conjunctive
a conjunctive normal form with
clauses.
implicit quantifiers,
Hello,
and it will have.
please
Uh,
come again.
Sir, it is a conjunctive normal form with implicit quantifiers. It will have at most of one positive literal.
Exactly. So thank you. So in horn clause, if we have the clause in conjunctive normal form, so there will be at most one positive literal, right? So in Prolog, the precondition of writing the rules that the rules they should be in a horn clause form, right? Other form of clauses they will not be allowed here, right? And so we talked about the goals. Now, while we are solving the problem, we'll see later that we want to match the goal that we have stated with the heads of the clauses so that we can apply the rule, right? So the precondition for applying a rule, what is the precondition? The precondition is that the head of the goal should be matching with the head of the rule. That in that way we can apply the rule. Now, while we are matching the goal, there are two operations that will be coming into picture. One is unification. You know what is unification, right? So I'm not repeating this. The other is substitution. The substitution is basically you are substituting variables with grounded literals or terms so that you have a matching goal, right? So these are the two things these are kind of bread and butter of Prolog. So these are the two things we need very frequently. And you know that these forms are basis of the computational logic. And you see that there is a very good connection between Prolog and this computational logic. Now, if we talk about features of Prolog, apart from the philosophy that we want to have a goal-oriented design, there are certain syntactic elements or any language, if we talk about, it has a set of syntactic elements by which we define the language and by which we write the programs, right? So I'll not be talking about the entire set of features because it's a very huge area. If you are interested, you can explore more on it. But I'll be focusing on the features so that we can at least get started, right? So the most two important things in Prolog, in my view, is the idea of recursion. So you'll see that most of the programs we'll be writing that will be based on recursion. So we'll be defining these rules in a recursive form. And the other important feature is the list. So we'll see that how we can manipulate the lists to achieve our goal. So these are the two things we'll be discussing very extensively And of course, I'll not be going through the nitty-gritty of the features, but the idea is I'll be describing a set of programs or problems which I like to model in Prolog. So first part is modeling, where I try to analyze how to solve it. Then I'll go for the implementation, right? That is the idea. There is another important feature which you call as control backtrack. So we understand that while we are performing search in many of the algorithms, there is a huge amount of, or maybe there is an amount of backtracking, right? So you start to follow a path, and after some time, you see that you have hit a dead end, right? So what do you do there? You go to a point from where you can reiterate your search or repeat your search, right? Reopen your search. So that is what we call as backtracking. Now, if you let Prolog to find out the solution, so it will do the backtracking in its own way. Now, it might so happen that you want to just have a solution, a single solution. If you see that the goal is satisfied for at least one path, you are happy. You don't want to go further. But what Prolog will do, it will go on exploring other paths of satisfaction as well. So if you want the program to break at the point where you have got the first satisfaction that you can do, and that you can do with control backtracking, and the feature to implement that is card. So these I'll not be discussing. This control backtracking I'll not be discussing. I'll be discussing mostly these two features. So I have tried to categorize the problems into two parts. One is the set of problems that are inherently recursive and the set of problems that are inherently non-recursive. So this is a kind of very, I'll say, fuzzy classification, in the sense that you can say that every recursive problem, you can have an iterative version of that. But if you look at intuitively, so uh, I think most important thing in programming is to have a very good intuition. So at a first go, you have to start with an intuition, and then you can further refine the intuition to make the program more efficient. So the programs that are intuitively recursive, I'm calling them as inherently recursive. So classic example of inherently recursive program is computing the Fibonacci series. So I hope all of you know what is a Fibonacci series. Other example is merge sort, which is a kind of sorting algorithm that is a divide and conquer algorithm, where you have a list, you divide the list into two parts, and you go on solving the sub problems, and finally you merge the solution from the sub problems to get the final sorted list, right? So I'll be discussing all these things later, how to model these in Prolog. The examples of inherently non-recursive programs are like, you are given with a series and you want to compute the sum of it. So you have a series of numbers like 1, 2, 3, 4, 5, 6, 7, 8. And you see that it is a classic case of using iterative program to do this. But you can see that you can really model this using recursion as well. The other example that we may like to talk about is finding a path from source to destination in a graph. Again, you can think this in an iterative sense, but again, you can have a very good recursive way of implementing this, right? So these are the kinds. So I'd say these are the things we'll be discussing this part, and of course, this entire part we'll be discussing. And the kind of philosophy that I'm trying to follow here is a lecture by demonstration. As we go on, we'll be demonstrating the features, and in that process, we will learn the features. So let me spend some time to talk about goal-oriented programming. So goals are various kinds. So one might be having sequential goals, but we are not talking about this kind of goal here. So let me see what kind of goals we are talking about here. So here you can see that you have an initial state where the blocks are arranged in a specific configuration. And what you want to reach a goal state, right? So this is the kind of goal that we are talking about, right? So we have a state representation of the goal, and from the initial state, you have to go to the goal state. And of course, we know that in the search problems, we have talked about these kind of specific goals, right? Or if you think about these adversarial games, there as a player, what you want to capture, say for example, the queen of the opponent, right? Now, you can talk about an action that is immediate, or you can talk about a plan of sequence of actions that will give you a reward in some point of time. But you have a goal here. The goal can be immediate, or goal can be bit far-fetched, right? Or the goal can be to answer a question. So this is a kind of example of how Prolog can be useful in solving grand challenges. So can any one of you recognize this? If you do, please let me know. The last figure, a picture. Oh,
The IBM Watson, right?
yeah. So do you know what IBM Watson is meant for?
I don't remember exactly, but I think weather prediction.
Okay, so let me talk a bit about IBM Watson, because this Prolog has been used there extensively. So this is a kind of, IBM, they set up a grand challenge for every 10 years. So the first grand challenge that was notable was the Deep Blue machine, which defeated the chase champion then, right? And the next goal they set was to have a question answering machine that can answer any question on any topic under the sun, right? So with that objective, they developed a program which is IBM Watson, which basically takes into account a huge corpus of natural language text and try to formulate an inference-based algorithm to come up with answers to specific questions, right? And as a goal, they set it to defeat the Jeopardy champion. Jeopardy is a kind of reality show in USA where it is a kind of quiz show where the opponent will be asked any question on any topic. So Watson defeated the reigning champion of this Jeopardy game, right? That is a very interesting story, of course. But again, as you said, that it is used in weather prediction, and yeah, finally it was used in many other real world application domain like healthcare, weather prediction, and many others. And the point that I'm trying to make out here is that Prolog has been used in this in developing this. So basically, we are interested in goal and we want to specify our intent using goal, right? So let us see what are the language choices. So one choice could be, okay, known languages like Fortran, C, C++, Java, Python, which we can use. These kind of languages, they are imperative, like say they are how type of language. So there we specify the exact procedure to solve the problem, right? So other choice is the goal-oriented language, which is kind of declarative. We just declare what we want to achieve. And these kind of languages are called what type language. Now, while people were searching for a language to implement AI systems, so at one point of time, Lisp was very popular. Though Lisp was not meant to be a goal-oriented language, so Lisp is a kind of functional language. It is a functional language. So anything you write in Lisp in a functional form, right? But this is what Patrick Winston has to say about using Lisp to design goal-oriented systems. So goal-oriented programming is like reading Shakespeare in language other than English. So AI community, they did not really bank upon Lisp to design these goal-oriented systems or AI systems in particular. And they resort to, or they invented this language Prolog, which is a truly what type language. right? So let me spend a bit amount of time to demarcate this imperative and declarative notion of language. So basically in imperative language, you have got procedural languages like C, C++, C, Python, etc. And you have object-oriented languages like say Java, C++. And under declarative category, we have got functional language like less, logic language that we'll be studying, which is Prolog, and query language like say SQL. So while you are writing database program, you have the data stored in set of relational tables, but while writing the query is where you just declare what you want to achieve. And that's why this query is belonging to this declarative language family. Here you don't need to specify how to really match the rows, columns in the database tables, right? So in summary, imperative language, we just specify a sequence of commands, which are basically procedures. And in declarative language, we specify what we just really want as a result, and we leave the detailed processing to the language or the language environment, right? So let me first talk about the connection between Prolog and first order logic, which we have given a very brief overview. So let us go a bit deeper into it. So as I mentioned earlier that horn clauses are the clauses that we write in Prolog language. So all the rules that we'll be writing in Prolog is a set of horn clauses. So let me tell you what we have in a Prolog program. So in Prolog program, we have the initial state or the current state of the system stated as a set of facts and a set of rules. And this set of rules actually define your programs. Right. So for example, the horn clause of this form, like child X and male X implies boy X, right? So how do you write it in CNF? So basically we'll be having this as not of child X or not of male X or boy Y, boy X, right? So you can see at least we have at most one positive literal here, right? And Prolog uses a proof technique. So here we will see that the solution to the intent that we have provided, the goal we have set, is met using a proof procedure. So we just try to prove the goal. So that is what we mean by solving a problem using Prolog. So solving problem in Prolog is basically trying to prove the goal. And the proof technique that we'll be using our very known technique, that is resolution principle, right? And I mentioned earlier that we need to have a goal matching procedure, right? So if we want to prove that, say Peter is a boy. So first we need to match this with the rule, right? So here we are doing unification. We are unifying the head of the predicate with the head of the this part of the rule, right? And we are trying to see whether the number of arguments are same in both the cases. And then finally we do a substitution of X by Peter. And you know that this is exactly we did in computational logic, in first order predicate logic, right? So let me state a kind of common confusion that might arise while we write Prolog programs. So the confusion is the way we represent the rules in Prolog program. So if you see that we are writing an implication in the form like child X and male X implies boy X. So what is the semantics of this? The semantics of this is if, so this is your antecedent, right? and this is your consequent. So what is the semantics of this? So if the antecedent is true and also this is true, then we infer that this total implication is true, right? Now I have a goal that I want to prove that Peter is a boy. So that is my goal. I want to set it to be true, right? Now, in order to set it to be true, what should be true? This child Peter and male Peter, this should also be true. So we are adding a sub goal here. And then we go on proving the individual elements in this formula, right? Now, the point that I'm trying to make here, that this is the original goal that we started with. And from this, we are having a set of updated goal, which is this one. So that's why Prolog writes this consequent in the first place and antecedent in the second place. So these should not be confused with implication. This is not implication. Implication is the other way around, right? So this is a kind of common confusion that may rise in the beginning, but over the time, if you have practice, then this will not be an issue, right? So this kind of thing that we need to be careful about a bit. So this is my goal. This is what I want to prove. And if I want to prove this, I have to prove this also, right? So any question at this point of time on anything? Okay. So with this, let us talk about the computational model that Prolog follows, right? So what we have got the program, which is a set of rules or clauses, right? And we, of course, we need to know the initial state, which is stated in a set of facts. Now, one thing that you need to consider that Prolog follows a closed world assumption. So can anyone of you tell me what is a closed world assumption?
It is like everything that is specified in the state is true and everything else is false.
Okay, great. Thank you. So we specify the initial state using a set of facts, right? Now what we have got the goal, which we want to prove this. So want to prove this. So what this Prolog execution will do, it will take the rules and the facts and repeatedly apply the resolution principle to come up with the answer. So what kind of answers we look for? So the first answer that we look for, whether the goal is satisfied or not, right? Now, if the goal is not satisfied, you just say fail. And if it is satisfied, then want the answers. And what are the answers? Answers are basically the list of substitution. So for example, here we had this boy Peter. We wanted to prove this, right? And in order to do that, we came up with the sub goals like child Peter and male Peter. And we need to check whether this is true. So if this fact is there in my initial state description, then it becomes true. And then it becomes true if this male Peter is also there in the set of facts. So what we are doing, we are substituting x by Peter. So our answer of running this Prolog program would be x equal to Peter, right? And if you have multiple variables in your goal, then all these variables will be instantiated and all the instantiation will be shown. Now, there might be multiple answers, right? So there might be multiple combinations of substitutions that will satisfy the goal. And in that case, you'll be having multiple solutions. So we'll see all these examples. So let us give some example of Prolog facts. So what you can see in the left-hand side in this white box is an academic genealogy of the person we know as Stuart J. Russell. You know him, right? So this AI book that you are studying is Professor Russell is one of the co-authors. So that's why I have picked up this person to illustrate this example, right? So what is an academic genealogy? Academic genealogy is basically who has advised whom. So for example, Marvin Minsky, which is who is kind of another big name in AI, has advised, say, Joel Moses, right? And Joel Moses has advised, say, Michael Gennesreth. And Gennesreth has advised Stuart Russell, and so on and so forth. So here, as a set of facts, we are stating the initial state combination or the world knowledge, right? So for example, I'm saying Minsky is an advisor of Moses, right? And like this. And finally, you're saying that Felix is a male and Dana is female, right? So this is how we have stated our facts. Now coming to rules, so let me define a rule called grand advisor of X. X is a grand advisor of Z. So how do we define that? We can define it very simply. We say that X advised Y and Y advised Z. And in that case, you say that X is a grand advisor of Z, right? So this, if you write this in first order logic, how would you have written this? So I'm not writing this quantifiers. So you would have written like this: advisor XY and advisor YZ implies grand advisor XZ, right? So yeah, writing in a different way in Prolog. So that you have to very conversant with as you go forward. So this part of this rule is called head, or the consequent part of the implication. And the remaining part, as you see, it is called the body of the rule, and it is basically the antecedent in the implicational form, right? And this part I have already written. So basically, this is how we read this. If there is a Y such that X is an advisor of Y and Y is an advisor of Z, then you say that X is a grand advisor of Z, right? So as I have mentioned earlier that Prolog rules are horn clauses and the horn clauses are of this form. So this is the most generic form of the rule that we are writing. So why you are saying this? Because we are having the disjunction as well as the conjunction. So let us see how to translate these into horn clause, right? So as I have mentioned earlier, Q will be my head. And this remaining part, the antecedent of the implication will be our body. So we'll be writing Q, then colon, and the remaining part. So let us see the form that we have to write. So this is what we have written. So this is the consequent part of the implication. And how do we write the antecedent part? We write this in this form like this. So this semicolon in Prolog means disjunction. And comma in Prolog means conjunction. So basically logical and this is logical or, right? So now you see that P11, P12 and P1m, they are disjuncted. So we have got P11 disjunction, P12 disjunction, etc. And followed by that, you have got these conjunctions here, right? Now, after the facts and the rules, let us spend some time on the recursion. So how do we have a recursive philosophy to write the program? So we'll be taking the same example. So first of all, we define the relation called ancestor relationship, right? So we say that X is an ancestor of Z. So how do we define this? So if X is an advisor of Z, then we can say that X is an ancestor of Z. That we can do, right? Also, if we see that X is a grand advisor of Z, then we can also say that X is an ancestor of Z, right? Of course, you can see that if this chain can go on, right? So the first chain is, say, X is an advisor of Z. The second chain is X is an advisor of Z and Y, and Y is an advisor of Z. The third chain I'm specifying is X is an advisor of Y, Y2, and Z. So this ancestral chain, this can be of arbitrary length, right? There is no control in that. So should we keep on writing rules like this? Of course, we should not, right? So what would be the best way? Can any one of you tell me?
So X is an ancestor of Z if X is an ancestor of Y and Y is an ancestor of Z.
So you are saying that ancestor XZ, that means ancestor
XY,
Y,
comma ancestor YZ.
ancestor YZ. So will anybody comment on this? So do you think this is fine?
So this is fine if we have the base condition that ancestor XY is also is advisor XY.
So ancestor XY is also, and so which we have already written.
Yes, so we have to have that and we can have this.
So again, with this, can we do better than this? So this is some way it's okay. So do we need this ancestor thing?
We can replace that with advisor.
Exactly. So we can say that ancestor XZ, advisor XY, then ancestor YZ. So you see that we readily understand the necessity of recursion, right? So that if you don't have this recursion, your rule base will be exploding like anything, right? You have to count the chain and you have to write so many rules. But if you use recursion, you have just only one statement to write, right? So that is the beauty of recursion, and that's what basically Prolog leverages, right? I think we have discussed this slide. Now the next question is, if we have this, do we understand how Prolog answers the question? Right. So let's say we have this question like ancestor Minsky Russell. So you want to see whether Minsky is an ancestor of Russell, right? So by the figure, we know that Minsky is an ancestor of Russell, right? So at this point, let me go to the demonstration, then we'll be coming back to this, right? So just try to remember that this is what we want to do, like Minsky is an ancestor of Russell. Okay. So you can see my browser, right? Hello?
Yes, sir.
Yes,
Okay.
sir.
So this is what I'll be using, and of course you should be using to write the Prolog program. So this is a cloud-based programming environment as you do like in Colab Notebook. So this is it has got two versions. One is directly you can write the program, and you can also have a notebook kind of sense as you do in Jupyter and other places, right? So here, let me first introduce you to this environment, and maybe that will not be taking much time. So in the left hand side, you can write your program, and the program you can have the set of facts as you can see here, and the rules that defines the program, right? And in the right hand side, you have got many places. The first place is important place is the goal. So you can see this question mark started with question mark and hyphen, right? So anything that starts with this question mark and hyphen in Prolog, it is a goal. So you have to write a goal in this form in any software that you use to run your Prolog, right? And then you can specify your goal here. And whatever result that you want, those will be coming in this part. So let me first run the simple program, then we'll be going to the other program. So let me check whether Dora is a boy or not, right? So we want to check boy. So if you run this, it will say false, right? But if you say Peter, it will say true. And for this small program, you can figure out yourself why this is true or why this is false, right? But if you have a very large program with number of rules which you have to write if you want to solve any real world problem, then this manual tracking would be very difficult. So for that, this environment gives you another facility which we call as the trace. So you say trace, comma, and within a parenthesis, you put your goal. Right? Now let me see what happens. So if you say run, now it will let you run the program stepwise. So your first goal is to check whether boy is a Peter or not, right? And in order to solve that, the first matching you'll be doing is the matching with this rule. And one thing that you need to consider that Prolog matches the rule using the sequence in which you have written the rule. And we'll see that the ordering of the rules also they have implication in the runtime of the program, right? So it has got only one rule. That's why it is matching this, right? Now let us go to the second one. So we have this sub goal like child X, and X will be instantiated with Peter because we have instantiated or substituted X by Peter, right? And child Peter is true by this fact, right? So this part is done. Then we'll be pushing the next goal to be male Peter, right? Now, if you try to execute this, we have this male Peter to be satisfied. Now, whenever you see that there is an exit with green color, that means we have a success of that particular sub goal or goal. Now, if you have satisfied these two sub goals, that means boy Peter will be satisfied. So boy Peter is satisfied, and that is our goal that you want to satisfy. So this will return true, right? Now, if you say Dora, then the first goal is boy Dora. It will go on to check child Dora. It is true, of course, by this fact. And you say male Dora, you do not have any fact as male Dora, and as we are in closed ball assumption regime, this fact is false, right? And you see that whenever a fact is false or a goal is not satisfied, then we'll be having a fail with red color, right? Then you have the failure here, right? So this particular part, upper part, will give you either the trace of the program or the result of the program or result of the goal, right? And after you have written your program, you can save this. So you can create an account. The account can be created using your Google or Stack Overflow account. And if you just say save, it will be saving the thing in your cloud. And of course, you can download it, right? So while you will be writing the program for the tutorial class, you need to write it here and download the file. If you say download, it will download a .pl file, and that .pl file you have to upload in the Google form that we'll be sharing with you. And another thing that in the same file you can write many programs, but that is not advisable. But for the sake of simplicity, so this file I'll be sharing with you. This contains all the examples that I will be using in this module. So I have written all the programs in the same place, but it is not advisable to do that for the obvious reason. So yeah, we need to run this. So ancestor, what was that? Minsky-Russell. So it is saying true because you know that they are related via that. Yeah. So Minsky is an ancestor of Russell. That is true. So basically, tracing the program is fun, and that is what you need to do very frequently because the recursion will come out of intuition in the first place. And it might so happen that you have not specified the base condition or the base step of recursion, or it might so happen that you have written the recursion in such a way that it has gone into infinite loop. So the trace facility of this software will help you to trace what is going wrong, right? So this example, this is a kind of very example trace of what is going on here. So this is, I'll not say the entire trace. This is a sub part of the trace. I'm just following where the goal has been satisfied, but there are other backtracking path which I have omitted here for the sake of clarity, right? So this is our goal. Minsky is an ancestor of Russell. So first thing what we can do, we can substitute X by Minsky, they say Z by Gennesret, and you just check the first rule, right? Whether, okay, yeah, so this will not be Gennesret, it will be Russell, right? So this is the first rule. We'll be checking the first rule, and the first rule will give us the sub goal to be matched, which is advisor Minsky Russell, right? And you know there is no fact that is there in the database which says that Minsky is an advisor of Russell. So we'll be returning a no here. So this path is false. So you cannot achieve anything here. Now what we can do, we can apply this rule, right? So with the same substitution like X by Minsky, Z by Russell. So we have got sub goals to be at X by Minsky, which we have done, and Y is an anonymous thing. We don't know what this can be, right? We just need to find one Y, that will do. And we have replaced Z with Russell, right? So now let us try with Moses. I can try with many other, like say, I can try with Dana, I can try with say Peppert, but let us check with Moses, right? So if we replace Y with Moses, so what is this? This is satisfied, so this becomes true. Now we need to satisfy this sub goal like Moses, whether Moses is an ancestor of Russell, right? Now, in order to prove this, there is no, so one rule that we can apply here, which will take you directly to check whether Moses is an advisor of Russell, which is not. So then we'll go on applying this rule, right? So if we apply this rule, we need to find one Y. So we have found one Y to be Gennesret. So your first check would be whether Moses is an advisor of Gennesret, which is true. Then we need to match or satisfy whether Gennesret is an ancestor of Russell. And from that, we'll go to the, we will be applying the first rule here, which will come down to whether Greenwich is an advisor of Russell, which becomes true. Now, this truth value will be percolating here, right? So this becomes true. And by virtue of this and this, advisor Moses becomes true. So the ancestor Moses Russells becomes true. And as ancestor Russell's Moses Russell becomes true, this two together will have this ancestor Y Russell to be true. And finally, we'll find this Minsky Russell ancestor relation to be true, right? So this is a kind of very crude trace of the program, right? So, so what we really did here. So if we try to analyze, so we started with the goal, right? The goal that we presented here in the first place. Then, so we start with the goal, with a goal list. Then we matched the goal with rule head. So we consider the first rule for which we have got the match. Then what do we do? Can anyone tell me? So if we have a match with the with one rule with the head, then what did we do? Yes. Abhishek Sharma. Hello.
Yes, sir.
So if we so we have these two steps. We start with the goal list. In the goal list, first we have this goal, right? Then we match this with one of the rules. Actually, the rules will be matched sequentially, right? So after we have a match, what would be the next step? So what do you think?
Sir, after having a match, we
Okay, so any other?
Sir,
Yeah,
we have to discuss.
Yeah. So any one of you. Okay, let me call Rituban.
So we add the goals of the goal. We match the goal, right? We add the conditions for the goal to the goal list.
Exactly. So in terms of Prolog rule, so this is our head. We have matched the goal with the head. So what we push the body of the matched rule to the goal list, right? So push the body of the rule in the goal list. And how long will keep on doing this? Any idea?
So till we reach the final goal.
Yeah, but how do we know that we have the final goal? So actually we are talking about these points. So what exactly? So the goal list is empty. And with this, we have got the algorithm by which we can execute the Prolog program. So which we are going to discuss next. So if you need, we can have a break for a few minutes. 5 minutes would be okay. Hello?
Yes, sir.
Okay, so good. We will start in 5 minutes then.